Hello students, we have had in the last module we were actually learning about the spreading sequences, and in this module we will mainly consider inside the generation mechanism of the maximal sequences based on the linear feedback shift register architecture. We saw this architecture in the last module. We discussed about it, that we have considered that we are having a 3-stage linear feedback shift register, where there are 3 memory stages, and the output of the stage number 3 and stage number 2 are added. This is a modulo 2 operation, which is basically an XOR operation going on. So, it is modulo 2 added, and we fed the output of this adder as an input to the stage number 1. The clock pulse was helping, and in the arrival of each and every clock pulse, the stored data was moving from the one stage to the next. The output we took from the stage number 3. We also saw the generation table, spreading sequence generation table in the last module. We are not going to repeat that table once again, rather we will try to give a general form of any linear feedback shift register, and we will try to give a mathematical equation for generation of the shift register sequence at the output. Let us start slowly. Any state of a linear feedback shift register after the clock pulse I has arrived will be given by this. So, this is the total vector. Vector is talking about the combination of what is the combination of all the stage values. The value of the each and every stage is written inside the bracket. I will say that it is not S1I, it is, if it is generalized, then it should be SJI, where your J is the name of the stage and I is the number of the clock pulse for which you are writing the value of the stage. Of course, if I write capital S0, he will tell what are the initial condition of each and every stage. Okay. So, with that concept, remember the clock pulse can never have a negative value, because we are starting at t equal to 0. So, I should have always value the greater than equal to 0. So, if this is the situation of at any moment after the arrival of the ith clock pulse, if I wish to see what are the values of the stages storing, then I will be able to see this. Now, if I try to give a mathematical formulation of the stage value of a independent stage, which is equal to SJI, what the way the value is stored in this typical stage is something like this. The value of Sj at the ith clock pulse is nothing but the value which was stored in j minus kth stage at the moment of I minus kth time, or I minus kth clock pulse. It means what? If I take an example, if I wish to see what is the value stored in the stage number 2, so here it will be this value of the stage number 2, say for after the arrival of the second clock pulse, what will be it? Then I will get here, it will be the value stored in the second minus k is actually the value kth time. If I am thinking it is instantaneous time earlier. So, whatever the value was here and whatever the value was here during the clock pulse time of the first one. So, what you are getting here is, if you see of the second clock pulse, what am I getting here? It is nothing but whatever was stored in the ith in the earlier stage at the k during the k stage back, during the kth clock pulse back. And situation is, this equation holds good if the k value is greater than 0 and definitely it should be less than I. So, when I am talking about the ith clock pulse, I can get the value stored during I minus kth clock pulses. K can never be greater than I, but k also should be less than the j, the number of the stages you are having, and definitely the stage where you are asking, that should be less than the maximum number of the stages you are having in your design. So, again this S0I, it denotes that the input that is coming to the stage number 1 after the arrival of the clock pulse I. If I think that AI is the output that I am getting at the output of the whole structure at the bit time I, then the output AI is always equal to the value stored here in the last stage. So, it is always equal to SMI. I hope it is clear. So, we have already defined what is the instantaneous value stored in each and every stage on the arrival of ith pulse, and we have also related this value with the preliminary stages and there with the occurrence of the corresponding clock pulses going back in, which is giving actually the trace of the previous clock pulses or the previous timing instance. Also, we are getting what is the value stored in the ith with the 0th position, and also what exactly is the output value, how the output bits are related with the last stored value. We will relate all these points in the next derivation. And see, if we are having that the state of the feedback shift registers, they are uniquely determining the subsequent sequences of the states and the shift register sequences. If we consider that there are the period of the generated sequence AI, it is the period is equal to capital N, then the smallest positive integer, then the period can be defined as the smallest positive integer for which the value AI plus N is repeating the AI value, that we have seen in the last table, that if for the value of 7 for a 3 stage linear feedback shift registers, after the 7th clock pulse the value has been repeated in all the stages, the value has been repeated. So, the period is defined as the smallest positive integer for which the AI plus nth value is repeating its AI's value. Now, if the m stages repeats, there are m number of the stages involved. Remember, as we have already discussed, the period can or never be greater than 2 to the power m, it should be always less than equal to 2 to the power m. If we are having a Galois field 2 elements, that means the symbols can have either 0 or 1, then we can have the operations like the modulo 2 addition or the modulo 2 multiplication. The binary operations would look like this. It is an XOR table, we all understand that is a 0 XOR z, 0 is equal to 0, 0 XOR 1 is 1, 1 XOR 0 will be 1 and 1 XOR 1 will be 0. And this is a multiplicative operation that we understand that it will give equal to 1 when both inputs are equal to 1. Here this operation is the modulo 2 operation. And the Galois field, so it is the field will be closed under this modulo 2 addition and modulo 2 multiplication, and both the operations will be associative as well as the commutative. So, this property comes holds actually and comes from the fundamental concept of the field, and it is the closeness of that field. All that point we will be discussing when we will go ahead with the Galois field mathematics. It also follows that this additive identity element for this Galois field 2, it will be the 0, multiplicative identity is equal to 1. If it is a Galois field 2, they are the identity element, multiplicative identity element and additive identity element. And by the virtue of the distributive law, we understand that if we are having the elements A, B and C, drawn from that field, if the field supports the distributive law, then there definitely A into B XOR C will be equal to A B XOR A C, and B XOR C into A, it will be also given by B A XOR C A. If the A B C can be either 0 or 1, and equality holds good between the subtraction as well as addition. So, you can also write that A XOR B equal to C can be also holds also good for A equal to B XOR C. The input stage to the stage number 1 linear feedback shift register, we can write it that it is the combination of all the stages independent Ck into Sk into I summation over all k to m is given you the S0I. Why is it like so? Ck is the feedback component. I mean, if the stage is contributing to the feedback logic, then the value of the Ck will be equal to 1. If the output of this Sk is not contributing to the feedback logic, then the value of that Ck will be equal to 0. For example, if I go back to our earlier figure, here actually the stage number 3 and the stage number 2 are contributing to the feedback logic. So, Ck value for C3 and the C2, they will be equal to 1, where the C1 value will be 0. And every cases, for each and every stage, you are looking into the independent value of it getting multiplied with the corresponding contribution towards the feedback, multiplying it, and then you are adding up such values from k is equal to 1 to k is equal to m, I mean 1 by 1 stage. The total combination is coming back as a feedback to the 0th stage. It is the we are writing, though we are writing it as S0, basically it is the stage number 1, and the input to the stage number 1 we are writing as S0. Once we have understood this fundamental concept, let us enter little bit in detail. As I have already mentioned, the value of the Ck is a contribution to the feedback. It is a feedback coefficient we call. Its value may be either 0 or 1 depending upon whether that typical stage is contributing or not. Remember, for the by default for the last stage, which is the feedback coefficient always is kept 1. If you do not keep it 1, then the final stage you do not have any contribution to the generation of the shift register. It will have simpler delay, 1 stage delay, and that can be proved actually in the last figure that we were talking about in the slide number 1, where as I showed that C1 value is 0, C2 and C3 values are 1, and hence your feedback to the input stage is a combination of the XOR operation of the stage number 2 and stage number 3. If your C3 at the last stage value is not supposed to be 1, then you try to do the exercise at home. You will see that the final output is just a shifted version, and there is no contribution of that final stage in the generation of the code happening. Now, the general representation of this linear feedback shift register, when we are giving the general form of the mathematics, the general form of the shift register, we can also show. In the next slide, we have shown the two different structure of the linear feedback shift register. Let us first concentrate on the upper one. So, now we have increased the stages up to the number small m, and here we are seeing that the Cm value is always 1, and depending upon the logic scenario you wish to add, some of the switches who are actually now controlling the contribution of the corresponding stage in the feedback architecture, they are either closed or they are open. If they are closed, their value will be, their corresponding C values will be 1, and if they are open, that means their corresponding value will be 0. And the corresponding stage will be contributing as a XORed, it will be XORed with the previous one, and the final XORed output will be fed back as the input to the stage number 1. Going by this, expression and explanation also we can come back. Now, we are now ready to develop slowly the output sequence. We understand the output value, output is equal to AM, and which is basically the direct value stored in the SMY, or the last stage of the value stored for the ith clock pulse in the last stage of the feedback shift register. And this holds good always whenever the I is greater than equal to M. When I is less than equal to M, you are basically getting the values which was stored in the initial situation. So, one by one the initial value will first come out. When I will go, the number of the clock pulse will cross the number of the stages involved in the design. Definitely you can think that whatever the last value stored is coming at the last stage, last memory stage, that will come out. And if I try to see the structure, then whatever the value coming in the equation, coming at the output, so it will be also getting stored in the as a input to the first stage also. How is it coming? The concept of this comes from the fact that this upper figure is not implementable easily and not hardware friendly. In order to make the figure hardware friendly and to increase the speed of this implementation and the processing of the data through the feedback shift register, we come down to this high speed form, where all the feedback path, it is typically one value, and all the modulo 2 operators, they are shifted towards the inside in between the path of the processing between one stage to the next. If this is the situation, then the value output here, whatever we are seeing as AI, and then AI will be basically whatever I am trying to see, that AI will be directly connected also with this input. But never mind, there we will come later, but currently what I am trying to see here is the value of the AI, what we are getting at the output, when I is actually less than M, for I less than equal to M, what I am getting at the output is basically the initial values stored one by one in the stages. So, at the first clock pulse, the stored value in the last stage, initial value of the last stage will come out. Second clock pulse, last but one stage's initial value will come out, and like that it will go on till you are reaching the value of I is coming equal to M. Then the first initial stage's value, initial stage value of the first memory or the first stage will come out. If I utilize this concept, then for I less than equal to M, AI will be always S0 I minus M. Okay. And if this is the situation, if I is like this, and hence I can substitute the value of the S0, because the value of S0 we have already seen in the last equation, in the last slide. The value of my S0 is given by this expression 1.13. So, if it is delayed now by I minus M, so it will be the same equation only changed by Sk I minus M, that we are substituting here in this place. And once this is there and we understand that the last stage value is basically the value of the coming output. So, Sm I minus k is finally can be replaced by A I minus k, and now actually you are getting a linear recurrence relation. Before I greater than equal to M, you are getting a linear relation, always you are getting a linear relation, that A I of this Ck A I minus k. And whatever you are getting for I less than M minus 1 is for A I it will be the value of the M I minus I of that stage. I hope it is clear. So, I repeat, then when the I is greater than equal to M, you are getting that M value stored, whatever was stored in the mth stage, and then I understand that the mth stage value whatever I got, it was actually the value of the which was fed as an input to the stage number 1 m clock back from the current clock I. So, I am writing A I is equal to my S0 I minus m. Then I substitute the value of S0 from the previously developed equation, which is Ck into Sk I minus m, and definitely from the last stage is equivalent to the output. So, we are coming down here, and this is a situation when I will be greater than equal to my number of the stage, clock pulse is coming exceeding the number of stage, and here if we are not exceeding stage, in between the stages we will get the m minus ith stored values for the 0, whenever whatever it was stored value for the 0th pulse. I mean, this is a initial situation or initial condition, initial value stored one by one in the all the stages. We will refer next onwards the high speed form of this generation, and we will proceed for our derivation. So, I have replicated that figure once again here for easy understanding of the derivation that is going on here. Remember that we understood that if we are changing the structure like this, bringing all the modulo 2 operator in between the stages and making the feedback path is equal to directly connected to the input, then at any stage S j I, I am getting the value of S j I by the S j I minus 1, I minus 1th stage value getting convolved with the corresponding switch value. This switch value is such that it is Cm minus j minus 1. You put a value, suppose if you are at j is equal to 2. So, 2 minus 1 you are getting the value stored in the stage number 1 for 2 minus 1 for the ith for first clock pulse. So, whatever the value was stored in stage number 1 during clock pulse number 1 getting convolved with your j is equal to was equal to 2 in our case. So, C m minus 2 plus 1. So, it is C m minus 1th value, and here you are getting the value of C 1 of course, and if you are having certain values here, you are coming from this side to this side. So, basically you are clubbing or you are basically taking the value of the last switch and his corresponding multiplication of this last Sm value, which was multiplied with this value of the switch. So, Sm I minus 1. So, everywhere when you are computing the value of the second clock pulse, you are getting the input from the stage number 1 stored in the first clock pulse, also the value stored in the mth stage during the first clock pulse multiplied with the corresponding weight vector which is contributed by the switch, and then the modulo 2 operation of these two. So, this equation holds good when your I is greater than equal to 1, and also for the j stage j from the second stage onwards, because for first stage this equation does not hold good. First stage there is a direct input from the last stage itself. And so, if I start like this, so for S1 for stage number 1 and the ith value, this will be directly from Sm I minus 1, correct. If I keep on repeating this first expression, so suppose I am trying to follow it for Sm. For Sm I will get Sm I minus 1, m minus 1th stage for I minus 1th clock pulse getting convolved with the first value of the C1 and Sm I minus 1. Okay. So, Sm I minus 1 and the multiplication of this C1, all that will be multiplied and coming beside. Similarly, if you Similarly, if you proceed for your Sm minus 1, it will be giving the same way the connection between Sm minus 2, and every time with the Sm minus 2 you are getting the input from Sm for the previous clock pulse and getting multiplied with the C2. So, like that it is proceeding, and at last whenever you are ending up, you are coming with the expression like this. And if I keep on substituting the values here, suppose in the equation of Sm I am substituting from Sm minus 1, and inside that Sm minus 1 I have the values from Sm minus 2, and from Sm minus 2 I have having values from Sm minus 3. If I go on like that, you will be ending up with Sm minus I getting substituted the value of S1 I minus m plus 1 finally, and all these values will be added up. So, there is a XOR operation with the summing up term of the Ck and Sm I minus k, with the Ck and Sm I minus k, and then this guy is moving from k equal to 1 to m minus 1. So, you are having the contributions from C1 to Cm minus 1, k is varying from 1 to m minus 1. So, Ck and Sm I minus k. So, that is the way the whole part is getting formed. Okay. So, for each and every stage now I know how actually the data is getting accumulated, and it is processed also slowly one by one. We understand that AI will be the final stage output will be from SMI only, and if I now substitute from 1.17 like this from here, and then you utilize this AI will be always coming out from the last stage, and if I substitute this value in the last developed equation here. So, where I will be ending up with is this AI, where what I have done, this SMI I have substituted with AI, because that is the understanding, because AI here is directly coming out from SMI, and this expression also can be substituted by some term of AI, and this is another portion remaining in terms of AI minus k. So, finally, I can relate the last state equation with the output sequence. And since I understand the Cm is always should be equal to 1. So, this equation basically is coming same as we have derived earlier. So, this is a proof that the high speed form can also generate the same sequence like the previous non high speed form. I mean, this circuit and this circuit will give you the same sequence, only difference is that this will give you this can generate the sequence at a very high speed. So, the two implementations now they are equivalent, that is the demand is, and however, this differential initial states and their different sequence states, they are really required for your successive generation. And if I keep on doing the successive substitutions into the first equation one by one, so what we will end up with is, when my clock pulse is varying between 1 to the less to the number of the stages, I mean 1 to m minus 1, when this is varying, then the expression will lead like this, because you are basically getting XORed with the initial state values of the previous stage, and substituting AI here for SM, AI is equal to SMI, and substituting AI minus k is equal to SMI minus k, all that. So, you will be ending up with Sj0, and using some binary arithmetic also for j is equal to m minus I, we will be ending up with J0, I mean the initial stage, and this is the equation ending up. So, SMI minus k will be governed by Sm minus j minus k with after all these substitutions, and there also I am coming from m minus I. So, I to j transformation has happened, nothing else. And now the last portion, we are trying to see whether we can highlight little bit over some properties of the generated sequence through this high speed linear feedback shift registers. Suppose you have generated two sequences from a same shift register. One sequence is A, combination of A0, A1 dot 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 dot, and the other binary sequence is there B, which is the combination of B0 to certain value. And we define that there is a binary sequence which is now generated outside by doing the bit by bit modulo 2 operation of the sequence A and sequence B. And we write that the newly generated sequence D is given by A XOR B, and the every component of the D, the ith bit, is generated by the bit by bit modulo 2 operation, as I told, for I greater than equal to 0. Now, consider that the sequence A and B, they are generated by the same linear feedback registers, but maybe the initial condition for generation of A and the generation of B, they are not same. If that is the situation, for the sequence this D, and using this associative and distributive law of this binary field, we can show that the value, each and every any bit value D j can be replied, can be actually obtained by taking this C k A I minus k XORed with C k B I minus k, and as this is the associative and distributive law we are applying. So, the sum will come out, and the independence, if I take C k A I minus k, will be XORed with C k B I minus k. I can take C k common, and then it is basically the XOR operation going on between A I minus k and B I minus k. So, A I minus k XORed with B I minus k is basically D I minus k. What's the final observation is, we understand that any jth instant data output which is of this newly generated sequence is also considering and also maintaining a recurring relation of its previous sequences. Previous sequences means whatever you are getting at I minus kth clock pulse. So, fundamental gist is, if you are generating a linear feedback shift register, the generated sequence keeps a linear recurrence and occurrence of the generated sequence. The generated sequence, all the bits will have a linear recurrence relation. Even if you are generating the two different set of the sequences who are having two different initial conditions, both of them individually will keep a linear recurrence, and a new sequence which is generated by the XOR operation of these two sequences A and B, he will also have a linear recurrence relationship with the generated bits. All the generated bits will have a linear recurrence relationship with the previous bits. Next module, we will see in detail a little bit more about the properties of these maximum length sequences.